My name is Leland Richardson, and I'm a software engineer working on Jetpack Compose. Today I'd like to talk to you about modifiers. And as the title of the talk suggests, I'm going to take a little bit of a deep dive, and that means that some of this content might assume a little bit of knowledge about Compose, but I'll try to do my best to walk you through it. Okay, so to start, I want to provide context on the design decisions that led to the current modifier design. And then I'm going to talk about how modifiers are getting used differently than we initially expected and how this impacts performance. Finally, I'm going to talk about some major work that's been going on recently. And this has really changed how modifiers have worked under the hood, and some new experimental APIs have showed up that we believe result in significant performance improvements. So some of you may have noticed that the first major milestone of this effort landed in the first beta of Compose UI 1.3. This was titled Modifier Node Refactor, and this was a completely backwards compatible change and should not have had any effect on your app, but it was the first step in enabling this major shift in modifier architecture. So first, let's talk about how we got to the current modifier design and what was considered along the way. So first and foremost, Compose was built to manage trees. And in Compose UI, the nodes of this tree are described by an interface called Compose UI node. We often refer to these as layouts or layout nodes, since in Compose UI, the only way to create them is through the layout composable. And as we can see here, modifier is one of the parameters that layout accepts. But let's take a step back and imagine that we're creating a UI toolkit from scratch, and we have no notion of what a modifier is or what we might use it for. So in our imaginary UI toolkit, we're going to probably have a base node type. And whether this is an interface or a class doesn't really matter. But there's going to be certain cross-cutting concerns that we're going to have to make sure that our UI can handle. So for example, we want users to be able to click or press on a node and then to be able to execute code as a response. So we'll add an on-click property. We also might want our node to have a background color. We want to be able to specify padding around the node to separate it from the others. And so we might play around with this for a little while. And then we might realize that, okay, well, padding might not be the same in all directions. So we update it to have one property for each direction. And as we kind of keep going down this path, we can start to see how the strategy might not scale. What if we want to not just have solid backgrounds, but gradients? What if we want not just an on-click handler, but an on-long click? Or better yet, a more general gesture system? So these types of cross-cutting behaviors are things that we want every node to be able to do. But there are so many things, and most of the nodes won't utilize almost any of them. So we learned from our prior mistakes, and we didn't want our base node type to have the weight and cost that was needed to enable all of these behaviors for every single node. So we started exploring other options. Another option we explored was instead to encode each one of these behaviors as a node in the tree itself. So in this case, padding, background, clickable, these were composables themselves and added to the tree. So with this approach, there's some syntactic overhead, there's a little bit of nesting of lambdas and things like that, but overall it works pretty well. The main problem with this approach was that each behavior composable then also had to have a content lambda parameter. And this is where its children would go. However, we were thinking of these things as single children composables. But there's nothing stopping you from sort of having multiple children. In Compose, composable lambdas can compose arbitrary content, and we didn't want that to change. So in this case, we have to answer the question, what happens when you put multiple children below clickable? Do we stack them vertically, horizontally? What? So in order for this to work, clickable would have to encode some sort of a layout policy in it. But layout policy isn't really something that we think of clickable needing to know about. And so in reality, we expect layout composables like row and column to be concerned with layout, but not any of the other things. And so in the early days of Compose, we kind of went with this approach, but it ended up being a little too error prone and confusing for users when this was an issue. And eventually we decided that all composables needed to allow for multiple children, and that everything needed a layout policy, and that was just how it was going to be. The other behaviors, we ended up deciding that it was okay for this to be passed in as a parameter, for these behaviors to be encoded in a thing that we ended up calling modifier. And so with this approach, one of the neat things that happens is that you're allowed to pull out modifiers as an expression and do a temporary variable, and then pass that into multiple layouts as a result. This is a pattern that we liked, but it's actually trickier than it might seem to make it work. Consider the case of clickable. Clickable has stateful behavior in it. If you think about it, it tracks touch up, touch down, has delays, and there's even ripple effects. So critically, if we end up passing clickable into multiple layouts, we need to make sure that that state ends up getting created per layout. It's possible for 2 ripples to be going on at the same time, for instance. And in order to handle this use case, we came up with a new API, modifier.composed. And modifier.composed allows you to define a modifier with a composable lambda factory, and that itself is a function that returns a modifier. And so in that lambda, since it's composable, you can leverage compose to manage state for the modifier that it produces. And the whole special thing about this API is that this ends up getting called per layout. So the state ends up being per layout like we needed. We do this by having a materialize API. And so this materialize call takes in a modifier, some of which might be composed modifiers. And then we end up returning a modifier that's semantically the same thing, but all of the modifiers have sort of been expanded by calling the modifier.composed lambdas. We then ensure that materialize gets called before every node that it gets applied to. And so then the modifier that ends up getting passed to the layout is the one that is fully expanded, and then the state for those modifiers is living in the compose hierarchy. So an implementation of clickable could look something like this, right? In this case, we're using remember to create some state, and then that state is going to have the lifetime of the node. And this sort of solved the problem, but it didn't do so perfectly. The modifier.composed API introduces a few performance issues. One of them is really about skipping. So even though we're using composition, one of the key levers that can make composition efficient is to be able to skip functions. But we can't skip functions that have a return type. And in this case, modifier.clickable has a return type because modifier.composed has a return type. And so every modifier that used modifier.composed would be unskippable as a result. And because the function that calls modifier.composed isn't composable itself, we can't leverage the compose compiler in order to cache the lambda that it uses. And this means that the resulting modifier will never compare equals with the one before it. This is a pretty big issue because modifiers being comparable is actually the only way for us to determine if something has changed during recomposition. So in this case, every modifier will look like it has changed even though it hasn't. This also meant that modifiers that were stateful required a lot of remember calls in order to make sure that state updated while other state didn't. Because these end up getting composed every recomposition, these remember calls kind of add up. And they ended up being more expensive during composition than we initially expected. But despite these issues, we kind of figured that modifier.composed would only really need to be used in a few special cases. We were wrong. So in practice, we've seen that modifier.composed gets used a lot. And it's really shaped the way how modifiers work in practice. So let's take a look at an example. Consider the small example of a counter. We have a column with 2 text nodes. One displays the count, the other has a clickable modifier. One way to think about this is that this will produce a tree with 1 column node that has 2 text child nodes, where each text node has a text property and a modifier property. Each modifier, so one way to think about modifiers is as a lens through which everything above it sees the thing below it. So we can think of clickable as being part of the same overall tree. and it has the child text node. And the reality is that Compose UI doesn't produce columns and text. It produces really just layouts with modifiers applied to them. And so in the same way, text isn't really a text at all. It's just a layout. And we can start to think of the unique behaviors of a text composable as really just being a layout with a text modifier applied to it. So this is, what we have here is like a pretty reasonable mental model to have for the resulting tree that Compose produces. But it's actually still pretty far from the truth. In reality, there's no single text modifier that we have. Instead, text is made up of several modifiers that are required to encode the behavior of a single text element. And likewise, clickable also isn't just a single modifier. Clickable ends up using several modifiers to encode all of the things that a clickable needs to do. And this still isn't really the complete picture. There's several modifiers here that would also end up using several modifiers as a result. And to be honest, this also isn't the full picture, but I ran out of room. So the result is quite a large tree, and it's composed almost entirely of modifiers. And so instead of building a tree of layouts, we're really building a tree of modifiers. Going back to our example, this tree was produced from some pretty innocent looking code with just a single modifier visible. If we go and look at this modifier, so modifier.clickable in this case, we can see that it called modifier.composed 13 times. It had 34 calls to remember, 11 side effects, and this all resulted in 16 modifier elements in the final tree. So what does that mean? Let's try and understand the impact of this. And let's take a better look at like what the life cycle of a modifier is and what the costs associated with them are. So we can take a simple example of this chain of 4 modifiers. And this modifier chain is going to get initially created during composition. While initially this modifier has 4 modifier elements, one, as we saw earlier, is a composed modifier. This modifier will then get passed around, and eventually it's going to end up getting applied to a layout node. And as I mentioned earlier, this is where we expand that composed modifier by calling that materialize function. So this will end up executing the composable lambda that was used to create clickable, and it's going to result in several more modifiers. And we can think of then the state that is built up during compose as living alongside these modifiers here. And as I mentioned, this isn't the complete expansion. This is actually going to get materialized called on a lot of them, and we're going to recursively kind of go down, build up a tree. And so just to keep the slide manageable, let's just abbreviate this by saying, we've got many modifier elements, a lot of which end up having state that live alongside them. And so after we're done materializing the full modifier chain, we call set modifier and apply the modifiers to the layout. And in this case, when the modifiers are applied, we end up allocating these sort of owning objects for each modifier. And we call these entities, and they're really an implementation detail, but in a way you can think of these objects that they're objects that manage the behaviors between the different subsystems and dispatch things to these modifiers. So in a way, this is what the resulting tree looks like from our initial composition. But that's only half the story. What happens when we recompose and update the tree? So let's say that this time we have 16 dp of padding instead of 10. So we've updated something. During recomposition, we end up reallocating the original list of modifiers. Eventually, we again reach the point where we need to apply this chain of modifiers to the layout. And like before, we call materialize, and we expand the modifier. And at this point, the state that was previously remembered is going to be reused for these new modifiers. So both the entities and the modifier elements on the layout end up getting disposed at this point, and we apply the new modifiers to the layout. And we end up allocating new entities to deal with these new modifiers. And so the key thing to understand here is that many of these modifiers need to have state. And that state, it's critical that that state ends up being per layout node, per layout that they're applied to. And there wasn't really any API to enable doing that except for modifier.composed, at least not until recently. So the recent major changes that I alluded to earlier are meant to address precisely this issue. So let's take a look through the example that we just walked through, but instead look at what this will be like when we finish the migration of modifiers over to this new modifier.node world. So this refactor included an addition of a new abstract class, modifier.node. This is an addition to modifier and modifier.element. It doesn't replace these types, but instead works in addition to them. And it's probably important to clarify that these APIs are still experimental, and we're still validating different use cases and ensuring that they have the right API shape. As a result, the rest of this talk isn't really going to go into the details of the API, but really just talk about the general idea. So let's take a look at that same example and walk through it. During composition, we allocated a new modifier chain. And critically, these are all modifier elements. Importantly, clickable would no longer be a composed modifier. Instead, all 4 of these are a new type of lightweight, immutable modifier.elements, which know how to maintain an instance of a corresponding modifier.node class. So eventually, we go to apply this modifier to a layout. And this is significantly cheaper than before. Since there's no composable modifier, before we would need to do a lot of composition at this point in order to materialize the composed modifiers into modifiers. Now clickable is just a single element, and no materialize is needed. So we just pass in the modifiers directly as is. At this point, each modifier element then gets a modifier.node, gets a create function called on it, which then allocates a modifier.node instance. These node instances are directly part of the hierarchy. And they have the same lifecycle as the layout that they're applied to. And as a result, these objects are ideal owners of state for the modifiers that need it, like clickable. So then what happens when we recompose? Just like before, let's imagine we recompose with 16 dp of padding instead of 10. We allocate a new modifier chain. And now that these modifier elements are immutable, we can very easily compare them. And this is important because if nothing in the modifier had changed, which is a pretty common scenario, then compose would have been able to skip early and might not even needed to apply the modifier at all. And so, but in this case, the modifier chain has changed. So we do have to set the modifier. And when we do that, compose then diffs the previous list of modifiers with the new ones. And each of them are comparable, and so we can update only the modifiers that have changed, which in this case is just padding. The rest of the modifiers were the same, so we simply do nothing for all of them. So if we go back to our early example, we can see that with modifier.node, we're able to get from a tree like this back to our nice mental model of something that looks like this. So as you can see, there are several benefits to doing this way. One is fewer allocations. We don't have to reconstruct the chain during materialize. The chains themselves are shorter, and we don't allocate entities on the layout every time we recompose. The other is that there's just less composition going on here. There's no need to remember state or use snapshot state to proxy updated parameters, and so there's a lot less overhead that comes along with modifiers. And then finally, the tree itself is just smaller. Modifiers like clickable result in a single node instead of 16. Subsystems that are traversing the whole hierarchy are going to have a lot less work to do. So this sounds nice, but what does this mean for you? So first, you can expect that in the next few releases, you might be seeing some pretty significant performance improvements. So that's good. Second, if you're using modifier.composed to create custom modifiers, then these new experimental APIs might be something that are worth looking into, especially as they stabilize. And third, it's important to understand that pretty much all of userland code won't need to change. This is a pretty big deal. When I first started working on this, I was pretty concerned. I was concerned that I wouldn't actually be able to make the changes necessary to do these performance improvements. And at Google, we try to be really thoughtful about what public APIs we put out there, and we only make public what's absolutely necessary. And so this can sometimes be really frustrating to developers like you because it feels like we're actively preventing you from using these useful APIs. But this was absolutely critical in enabling us to essentially rewrite the whole modifier system. And that's maybe the single largest API service in Compose. And so to do it in a completely backwards compatible way is a really great thing. And I'm really glad that we were able to do that. So I'm going to end and just say stay tuned. We're going to continue working on this and let us know if you end up seeing any performance improvements as a result of this or any issues that come along. I'm going to be around all day to talk about this if any of you have any questions. And that's it. Thank you.